So in this video we're going to be starting grade 12 calculus. So we're going to start by rationalizing denominators of radicals. I should put that somewhere in regards to radicals. So let's start with an example. There's just a couple of rules we need to get down before we actually get into all the good stuff. So let's say we have 3 over 4 root 5, and I basically want to simplify this, and the way I'm going to do that is by rationalizing the denominator, and that I will do by, well, basically I'm going to we'll get rid of this root from the denominator. I want that to be a whole number, and that in the future we'll basically taking out roots and basic square roots, cube roots, any type of roots or exponents that we don't want in the denominator. Removing them from the denominator will make our lives so much more easier. So what I'm going to do is basically say that this expression is the same even if I multiply it by root 5 over 5. So if I was to continue with that, I should get 3 root 5 over, remember when you multiply root 5 by root 5, so 5 root 5 is basically 1 over 2 times 5, 1 over 2, and when I multiply when I multiply these two, the exponents add, so it's basically 5 to the 1, which is 5. So I'll have the 4 still. And then I'll have the 5. Which leaves me with 3 root 5 over 20. Okay, so let's move on to another example. Let's say we have a situation where the denominator is like this. Say we have let me just move this down. So, what can we do here now? So, if you have a denominator with 2 radicals, we are going to introduce something, well, not introduce, we're going to remember something we did in the past, which is basically multiplying conjugates. So, what do I mean by this? Let's just use ambiguous. Let's say root A plus root B. If I want to rationalize this, basically turn this into a real number, I can multiply this by its conjugate, which is just the same expression except subtraction. And if you remember why actually can do those cancel and you're left with a squared. Sorry. Minus b squared. That's why we multiply by its conjugate. So in this case, how can I get rid of this? Oh, there. In this case, root 6 plus root 3, I can multiply that by this expression, root 6 minus root 3. But I don't want to change the expression, so I'm basically multiplying this expression by 1. But this, multiplying it by its conjugate, will allow me to turn it into root 6 squared minus root 3 squared, which is also like root 6 squared is 6 and root 3 squared is 3. So I can basically write 6 minus 3 in the denominator, but I still have the root 6 minus root 3 in the numerator. I can't forget about that. So basically the denominator will be 6 minus 3, which is that. Oh no. So let's try another one. Let's do simplifying this 5 over 2 root 6 plus 3. So basically I'm going to, let me just get rid of that. Let's remember what we did from our last one. What we can do here is multiply the denominator by 2 root 6 minus 3, because here's plus 3, by its conjugate. And that should give me, well, in the denominator 2 root 6 squared is basically, let's multiply that out. 2 times 2 is 4. And then we have 6 times 6, which is 36. Okay. So we should have 4 root 36. 4 root 36 minus 9, because of our difference of squares. And the numerator, I should still have 5 times that. Well, I can open that up. 5 times 2 root 6, or you know what, simplest. The square root of 36 is actually 6. So 6 times 4 is 24 minus 9. So that gives me, 24 minus 9 is 15. And 5 over 15 is 1 over 3. So I can get rid of this. So I'm left with 2 root 6 minus 3 over 3. And there we go. We just rationalize another one. So let's try something else. Let's try this. No, I'll go with in this example, I want to rationalize not the denominator, but rather the numerator. So, we're going to approach this the same way we did the other ones by multiplying the numerator by the conjugate. Root 7 minus root 3 over 2. I'm going to multiply it by root 7 plus root 3. And that will give me 7 plus 3 for the numerator. Oh no, wait, sorry, not plus 3, minus 3. Our difference of squares. And then in the denominator I'll have 2 times root 7 plus root 3. So, what did we learn? Some key ideas. If we have root A over root B, that's the same as multiplying. This is from our first example. And then the second thing that we did was 1 over, say, rationalizing a denominator. If we have 2 terms, we can rationalize that by multiplying it by its conjugate. Which leaves us with root A plus B over A minus B. And there you go. Very simple things to remember, but it will take you very far in calculus. You'll have to know how to do these on the fly. So I'll end this video here. Actually, if you want to try one on your own, try to rationalize this one. minus root 2. This one down here might be a little advanced. And put your answer in the comment section and let's see what you got. Anyways, that's all for this video, and I shall see you in the next one. Okay, so in this video we're going to be looking at limits. So, what do we mean by a limit? Let's say you have a function, whatever it is, whatever it's doing. Say we want to know the limit at this point, how the function behaves as it approaches. Say we have this f of x, and we want to know the limit of f of x, what that's equal to as x approaches a. And let's say this is the x value where a is going to be approaching. So let's say that's the x-axis and that's the point a, or the value on the x-axis a. And I want to know as it gets closer and closer, here and here and here and here, as it gets closer from both sides, what happens to this function? So, by finding the limit as x approaches a, like we don't even need to consider what happens at f at a, because we don't even need to know that. The only thing that we are interested in with limits is the behavior of f of x near a. So, let us look at an example, fresh off of what we were talking about. Let's find the limit of this polynomial 3x squared plus 4x minus 1 as x approaches 2. So, what we can do is actually plug in this 2 into this equation. So 3 times 2 squared, which is 4, is 12 plus 8 minus 1 equals 19. So we can say that as this function, this polynomial, as it approaches 2, the function is going towards, like that is what the limit is, 19. And by limit, I mean that say this is 19. That's the point that we're looking at. And that's the function. Let me make this. Say that's the point. As the limit approaches that, as the function approaches x, I messed that up too. So let's say this x equals 2. 19. So just before it gets to it, it's going to be a slightly different number than 19, and even on this side, it can get closer and closer and closer from both sides. That's what we mean by the limit as x approaches that value. Before we start another one, let's just do some defining. Some properties. So let's say we have limit of k as x approaches a, and k is a constant. This is the property for any constant k. Limit of a constant, say k is a constant, the limit of it as x approaches a, then the limit is equal to k. Similarly, limit of x as x approaches a is equal to a. And let's just define some other ones. We might actually use these in this video. Let's say we have f of x and g of x. If we are adding or even subtracting it, these two functions, the limit of these two, x to a, so that is a property. So if you're adding these two functions, the limits are also equal to adding the limits of each one individually. Similarly, if you have a limit as x goes to a, for, let's say we have a constant c times f of x, that will also be the same as taking the c out and multiplying it to the limit of just f of x for any cent c. And how about let's say we're multiplying two functions. The limit of that is the same as saying the limits of just like that. These are just properties that will help us in the future. let's say we have it's good to kind of memorize these. They're not that hard, just simple rules. That one's easy, a constant. That one's fairly simple too. These are just rules. Adding two functions, the limit of that result is the same as the individual ones. This one's with a constant just comes out. Multiplying two functions and finding their limit is the same as finding each one individually. And then the division one is also similar. The limit as x goes to a for f of x divided by the limit as x goes to a to g of x. Oh, and also here, g of x cannot be 0 at all. Sorry, not g of x. The limit of cannot be 0. That's the one we need to go for. And one last one, which we should already have seen coming. Say we have f of x to the power of n. This is also the same as saying the limit as x goes to a of f of x to the power of n. That's for any rational number. So now we can actually go ahead but the limit can be applied internally from our exponent rule here. Basically, I took out the exponent of 1 over 2 out, and I'm left with this limit x to the 5, x2, x approaches 5, x squared over x minus 1. But here I can use my division rule. And I'll have the limit. Oh, it's gonna be a lot. So, limit x to 5. Why do I keep writing that? Of x squared over the limit as x approaches 5, x minus 1. And if I plug in the 5, I should have 25 over 4, which is 5 over 2. And that is my limit. Let's try one with that is not going to be as straightforward. Let's say we have x towards 3. Let's say x squared minus 2x minus 3 over x minus 3. Okay, so as you can see, we have a problem here. If I plug in 3 into the denominator, I'm going to get 0. And you do not want the denominator to be 0. So, in this case, what I can do is actually factor the polynomial in the numerator, which should give me, I'll write it here. I should be able to use x plus 1, x minus 3, and I have x minus 3 in the denominator as well. So that will cancel, and I'm left with x plus 1, which is equal to well, if I plug in 3, I should get 4. So the limit here is 4. But if you just went straight for plugging in, you would have got an undefined number. Let's do one where you actually have to x to the 0. So here, we cannot plug in 0 into this equation because the denominator will be 0. But what we can do is a technique that we learned earlier, and that is to rationalize the numerator. So I'm going to do that here. X plus 1 minus over And that should leave me with x plus 1 minus 1 over x times x plus 1 plus 1. And now that I have that, the plus 1 and minus 1 will cancel, leaving me with x over the x will cancel, leaving me with 1 over root x plus 1. Well, x plus 1 under the root plus 1. And if I plug in this now, my limit, I should get 1 in the numerator. Here I should get 0 plus 1, which is 1. Square root of 1 is 1. 1 plus 1 is equal to 2. So my limit is 1 over 2. So I think that is a good place to stop in this situation. Guess we did a lot of things. I can give you a parting gift of evaluate that. Let me know what you get in the comments. And that's all for this long video on limits, and I shall see you in the next one. Okay, so in this video we're going to be tackling derivatives. So derivatives really is the first, I want to say, half of calculus. And what derivatives basically means is, well, one of two things it could mean. Why does that keep happening? The slope of the tangent line. And remember, we have done many, well, we really went in depth into express this f at a, that apostrophe you see there, that is how we represent the derivative of f of a. And basically we can say that is f prime of a. Okay, so let's just write that out. So let's try doing this. Let's start off with an easy example. Let's say f of x is equal to x squared. Find f prime of x. So from our formula, we're going to put that in. So f at a, let's write out our formula here. Actually, the question was incomplete. That's what the question is. Find f prime if find f prime of x if f of x is equal to x squared at x equals 3. So let's use our definition. F prime at 3 is equal to -3. That's the example we're doing. So there we go. Now let's start plugging in our functions. So since our function is x being squared, and here our x is -3 plus h, so let's just put -3 plus h here, squared minus -3 squared over h. So let's start solving that. Let's expand that one. So -3 squared is 9. I should have -3h and -3h, so minus 6h, and then h squared. -3 squared will give me 9, but I'm subtracting that 9. Denominator still stays h. I forgot to put this here. Bad habit. be left with h plus 2x over h. My h's cancel, and I'm left with h plus 2x. And now, when I plug my limit in, the h is 0, and I'm left with 2x. So, for my f of x being x squared, my f prime of x is 2x. And that is how we use the super long formula. To find out the derivative. But in the future videos, I will show you an easier way. But for now, that is going to be all for this video. Actually, if you want to try one on your own, you can try to find this of f of x is equal to x squared plus 3x plus 1. Find the derivative. Find the value of the derivative at a equals 3. So plug in a into it. But yeah, I want f prime of 3, basically. So good luck with that, and I'll see you in the next one. Okay, so in this video we're going to be looking at derivatives of polynomial functions. So, if you remember, a polynomial can have this, and this, different degrees. You can even have 2x cubed plus whatever. We're going to learn how to do the derivatives of these polynomials without having to do the whole x. Without that entire process. is, I hope I pronounced that right. But yeah, so the derivative of a constant will be equal to 0. And like you can actually prove that by simply doing this. If I was to plug in like this constant, if I was to put it into here and do it the long way, this is incorrect. It should be H. F. Oh, F of. Well, we can't exactly plug in this x plus h into anything because if our function is just, k, all you really have is k for the function. There's nowhere to plug in a variable. So, in both cases, you have k minus k over h, so it's just 0. So, let's just move on into the next rule. This is called the power rule. And this is going to come in handy for all these ones. So, the power rule. This basically states that if f of x is equal to x to the power of n being the exponent, and n is a real number, then f prime of x, the derivative, will be n times x to the power of n minus 1. So the easy way to remember this is that the n comes down and you subtract 1 from the exponent. Let's just write this in the Leibniz format too. So we have that one, and I guess you could try to do it in an example, like say we have x to the power of 7, then f prime of x is equal, the 7 comes down, we have our x, and then our exponent gets subtracted by 1. And let's try it. Let's say we have 1 over x cubed. And that's the same as saying x to the power of negative 3. So g prime of x is equal to, first this comes down here, negative 3 x to the power of negative 3 minus 1, which is negative 3 x to the negative 4. So this x to the negative 4 can actually go to the denominator. So I have negative 3 over x to the 4. That's my derivative of x. If x is equal to 1 over x to the power x to the power of 3 over 2. Then our derivative is going to be the 3 over 2 comes down, and I'm left with x, and then I have to subtract 1 from the exponent. So if you subtract 1 from 3 over 2, you're basically subtracting 2 over 2. So you're left with 1 over 2, which is the same as saying 3 over 2 root x. And let's look at one more very important one. Let's say f of x is equal to x. Now when you just have an x, the exponent is actually 1. So if you were to take the derivative of that, the 1 would come down, and then you'd have x to the power of subtracting 1 from that exponent is 0. X to the power of 0 is equal to 1. So f prime of x is actually equal to 1. And that's going to be very interesting when you have just an x. So say you have in a polynomial 10x, your f prime of x is actually going to be 10. So that is the power rule. Let's look at this one. Now the constant multiple rule. And that's actually where this comes in as well. I guess that is that kind of. So if you have, let's say you have f of x is equal to k g of x, where k is a constant, then f prime of x is equal to k g prime of x, which can also be written by so by that logic, you can actually do this. The 3 is going to come down, and I'm going to have 3 times 7 x to the power. Well, let's go step by step actually. Using this logic here, k in this case is the constant, and g of x will be this x cubed. So this 7 will be put aside, and I'm going to find the derivative of x cubed. So the derivative of x cubed alone, the 3 comes down, and I have the x, and then I subtract 1 from the exponent. I'm left with 3x squared, which is also, once now I can multiply it in, 21x squared. That's my f prime of x. Similarly, if you want to do x, and then I subtract 1 from the exponent, which will be, if I subtract 3 over 3, I'll have 1 over 3. So I have 12 times, well, I guess the 3 I can get rid of the 3 here by turning that into a 4 times by doing that. So I'm left with 16 cube root of x. And that is the constant multiple rule, where I can have this multiple in front of it and just find the derivative of that and multiply it by that constant. Let's do the sum rule next. Which is basically, say you have p of x. Let me write out the whole thing. Say we have f of x, and that is equal to p of x plus q of x. And these two functions both of these functions are differentiable. Then f prime of x will be equal to p prime of x plus q prime of x. And yep, that will be written like this. And while we're here, we may as well just define the difference rule, which is basically the same logic, except when we're subtracting. revise some of the old rules that we have. We're going to take the constants out. So our derivative of x squared is actually going to be the 2 comes down, the x is there, and the exponent gets subtracted by 1, so that'll be 1 here, which is just itself minus, and in this case we have the 1 over 2 comes down, the x, and we subtract 1, so we're left at. So now now we can just simplify. 3 times 2x is 6x. And then we have on this side negative 5 over 2 x to the negative 1 over 2. Or you can simplify that. Well, not really simplify, or just rewrite it as 5 over 2 root x. And I guess we can do, say we have y equals first thing we're going to do is expand 9x squared plus 12x plus 4. Let's take the derivative. I have a 9 here, and then that's going to be my constant. I'm going to take my derivative of just the x squared, which will give me 2x. My 12 stays. It's a constant rule. My x will do the derivative of the x. So the derivative of x is just 1. We know that. And this is a constant, so we know the derivative of a constant is 0. So obviously this method of doing derivatives is so much easier and quicker than our last video where we wrote out the full form and took the limit as h approaches 0 every time. I recommend getting a lot of practice doing this, because you have to be able to look at this and very quickly write this out, like in your head. Like you can skip these steps. Like you have to be able to do this without writing it out. Just quickly, just by looking at this, see that the 2 comes down, that becomes 18x, that becomes 12, and there's a 4's gone. You have to be able to do that in your head, because calculus will get much more heavier in the future. But yeah, I won't scare you now, but go ahead and try. Say f of x is equal to negative x squared plus 5x plus 8. Go ahead and find out the derivative and throw your answer into the comments section. And that's all for this video, and I'll see you in the next one. Okay, so let's get into today's video about the product rule. So we're going to derivatives, but today we're going to learn the product rule. So let's say p of x is equal to f of x times g of x. Now these two are multiplying by each other. So when I want the derivative p prime of x, the derivative is going to be this rule. You take the derivative of the first function, f prime of x, and you multiply it by simply the second function, g of x. Then you add f of x times the derivative of the second function, g prime of x. So, if you want to write it in the Leibniz format, you can do if u and v are functions of x, dx of u times v is equal to derivative of u with respect to x times v plus u times the derivative of v with respect to x. So let's actually put that into an example. Let's say we have so what we can do is say that this is f of x and this is g of x. So, but let's just quickly find the derivatives of each of these. So, if f of x is equal to x squared plus 5, f prime of x is equal to the 2 comes down, and I'm left with 2x, the constant becomes 0. G of x is equal to x plus 5, but g prime of x is just, that's 0, and then the x becomes 1. So if I wanted to rewrite it in the formula v prime of x, f prime of x times g of x plus f of x times g prime of x. So f prime of x is equal to 2x. G of x is equal to x plus 5 plus f of x, which is x squared plus 5 times g prime of x, which is 1. And when you simplify that, you should get let's say 2x squared plus 10x plus x squared plus 5. Simplify that, you get 3x squared plus 10x. Am I missing something? x squared. And then you would have had 5 times x plus 5x plus 25. So this would be x cubed plus actually wait, that's it. So your p of x would be this if you expanded that, and if you were to do the derivative of that entire polynomial, you would have had 3x squared. Because the 3 comes down and you subtract 1 from the exponent, and then you have 2 times the 5, which is 10, and the x gets exponent of 1. And then you have the 5x, and this would become 0. So that is equal to that. I forgot that 5 over there. Anyways, let's try another one. Let's do h of x is equal to x squared minus 3x times x to the 5 plus 2. Now let's say the first one, f of x is equal to x squared minus 3x, but f prime of x equal to 2x minus 3, because x squared becomes 2x and the negative 3x becomes negative 3, and my g of x is going to be x to the power 5 plus 2. So g prime of x is going to be, the 5 comes down, 5x to the 4, and the 2 is a constant, so it's gone. So if I was to write this out, h prime of x is going to be f of x, which is x squared minus 3x times the derivative of g of x, 5x to the 4 plus f of x. Okay, I may have written this backwards. Let me just move that over. So I should actually write my f prime of x first, right? Because I want my f prime and then my gx, which is x to the 5 plus 2. And then I have my f of x, which is x squared plus x squared minus 3x. And then I have my g prime, which is that. So now, if I simplify this, I will get let's start opening it up. 2x to the 6 minus 3x to the 5 plus 4x minus 6 plus 5x 6 minus 15x to the 5. And if you collect like terms, That's what I want to find. So let's write out our, say this is our f of x. Is equal to 5x cubed plus 7x squared plus 3. Our f prime of x is equal to 15x squared plus 14x, and our g of x is equal to x squared plus x plus 6. Our g prime of x is equal to 4x. Yeah, well, 4x. And then our x becomes 1, our constant is gone. So, if we were to write it out using our product rule, first we would write our f prime 15x squared plus 14x. Oh, that's a big gap there. Plus 14x times our g of x, 2x squared plus x plus 6. Now, our second portion, we're going to write our f of x, 5x cubed plus 7x squared plus 3 times our g prime of x, 4x plus 1. And now, instead of simplifying, expanding and simplifying, all I'm going to do is just plug in negative 1. So I should have 15 negative 1 squared plus 14 negative 1 2 to the negative 1 squared plus negative 1 plus 6 plus 5 negative 1 cubed plus 7 negative 1 squared plus 3 times 4 negative 1 plus 1. So if we evaluate this, that'll become a positive 15, and that'll become negative 14, so that'll be a 1. This one will be 2 minus 1, which is 1, plus 6, 7. And then I have here, this will stay negative 1, so that'll be negative 5 plus 7, which is 2 plus 3, 5. Here I have negative 4 plus 1, which is negative 3. So I have 7 minus 15, which is going to be negative 8. And that's how easy it is to use the product rule. So let's do one more thing. This is called the similar or like related power of a function rule. This basically is going to cover you if you have a, say, f of x equals to x plus 1 with a power, like, and you want to do the derivative here. So the rule of thumb here is that if you have f of x actually, let me use a better example here. Let's say I have a function u, and u is a function of x, and n is an integer. So let's say u to the power of n, and u is a function of x, and let's say you want to do the derivative with respect to x. So the derivative of u to the power of n is actually n times u to the power of n minus 1 times the derivative of the function u with respect to x. So we can actually try that here. Say we have x, h of x is equal to x squared plus 3x plus 5 all to the power of 6. So h prime of x is going to be, let's just put that in here, 6 times the same function u, x squared plus 3x plus 5 to the power of n minus 1. So n was 6 now. It is going to be 5 times the derivative of u, which is going to be 2x plus 3. And that's how easy it is. These are just rules that'll make our lives easier. Let's do this one. Say f of x is equal to 2x plus 5 divided by 3x minus 1. So this can actually be rewritten as 2x plus 5 times 3x minus 1 to the power of negative 1. And this is where it's going to get really big. So let's actually, I'm gonna call this p of x, and then I'm gonna write this out. F of x is equal to 2x plus 5. F prime of x equal to basically x. Sorry, no. The derivative of 2x is 2. Okay. And then our g of x, which is the second term, is 3x minus 1 to the power of negative 1. But our g prime of x that will be equal to, remember we wrote it here in the rule, so the exponent comes down because we have the power rule, so negative 1 times 3x minus 1 times the derivative of this function, which is 3. So let's put this all into the product rule. P prime of x is equal to f prime, which is 2, times this 3x minus 1 to the power of negative 1 minus, plus 2x this can go to the denominator. And then here I have the 3 and the -1, so that'll be -3. Actually, I forgot this exponent right here. That is -1. So I have a -3, and in the numerator I have this 2x plus 5, and the denominator I'll bring down this 3x minus 1 squared. And if I multiply this side by 3x minus 1 over 3x minus 1, so and then I'll expand the numerator there. I'll multiply the 3 and so 6x plus 15 over 3x minus 1 squared. And so the numerator will become 2 times 3x, which is 6x, and then that'll be minus 2. Here I'll have 3x minus 1 subtract 6x plus 15 over 3x minus 1. Sorry, forgot the squared. So simplifying all that, 6x minus 2 minus 6x minus 15. That'll give me 3x minus 1 squared in the denominator. And I should be left with 6x minus 6x. So I have -2 minus 15, so that's -17 in the numerator, and I have 3x minus 1 in the denominator. And that's that. And if you want to try it on your own, you can try using the product rule to do this 3x plus 2. A little homework for you, 2x plus, and find the derivative, h prime of x. And if you want to use both that product rule and the power rule, you can try h of x is equal to x squared minus 9 to the power of 4 times 2x minus 1 to the power of 3. Find me h prime of x. And yeah, that's all for today's video, and I shall see you in the next one. Okay, so in this video we're going to be tackling the quotient rule. So just to write out the quotient rule, we're going to have h of x is equal to f of x over g of x. So if we have h of x equal to that, so our h prime of x will be equal to, and this one's going to be a long one. We're going to have our derivative of our first function, f of x, f prime of x, times the denominator, g of x, minus the numerator, f of x, times the derivative of the denominator, g prime of x, all divided by g of x and the denominator squared. So with that in mind, we can actually try to do this which is 3 times g of x, which is x squared plus 5 minus our f of x here. So we have 3x minus 4 times our g prime of x, which is 2x, all divided by our g of x squared. So our denominator squared, so x squared plus 5 squared. So now all we have to do is simplify this, and that can be done simply by expanding here in the numerator, so 3x squared plus 15, and that'll become a negative, so minus 6x squared plus 8x all over x squared plus 5 squared. And we can simplify this, negative 3x squared plus 8x plus 15 over x squared plus 5 squared. There we go. Let's do another one. Let's say we have y equals 2x over x squared plus 1. So our numerator is, say, our f of x is equal to 2x, our f prime of x is equal to 2, our g of x is equal to the x squared plus 1, our g prime of x is equal to 2x. So we can do y prime, or easy calculus really is. So let's do another one. Say we have f of x equals 2x plus 8 over root x. So let's write out f prime of x is equal to the derivative of the numerator, which is 2 times the denominator root x minus the numerator 2x plus 8 times the derivative of the denominator, which, x to the power of 1/2 becomes 1/2 x to the power of negative 1/2. And the denominator will be root x squared. So we will have 2 root x minus, that will become a fraction because that goes to the denominator. So that'll be 2x plus 8 over 2 root x all over, well, root x squared is just x. So continuing on, we can multiply. Now, how can we fix this? I guess we can multiply both sides of this numerator by root x over root x. Yeah, I think we could do that. At which point that will become 2x over root x minus actually wait. I could actually factor out a 2 here. So that'll be 2 root x minus x plus 4 over root x over x. So I took out the 2 from there. That leaves me with, if I multiply this by I have root x here. So that will come down. So I'll have 2x minus, oh sorry, 2x minus x is just x over and that is my solution. And there you have it. One thing that we should mention is that from this rule, g of x cannot be 0 ever. Otherwise, the denominator becomes 0 and becomes undefined. So yeah, that's all for this video on the quotient rule. Hope you enjoyed. And well, I forgot to give you guys a challenge, so you can do h of x is equal to x squared minus x plus 1 over x squared plus 3. Let me write that again. X squared minus x plus 1 all over x squared plus 3. Try that for yourselves and put it in the comments, see what you get. But until next time, that's all for this video. I shall see you in the next one. Okay, so in this video we're going to be looking at the chain rule. So the chain rule helps us with composite functions. So if we have, if we have a function in which we have, say, x, and that x, well, g of x is our function that we have. Composite functions let us combine functions, so we can say f of g of x. So our composite function h of x is equal to f of g of x. We can say that this is our composite function. So that would be, well, you can note it as like such, f times g. That is a composite function, which basically means this right here. So, given two functions, f and g, the composite function, which can be written like that, is actually f times g of x is equal to f of g of x. That is a composite function. So we're going to look at the derivative of this function. So let's just say we have a function let's say we have our function h of x is equal to our composite function. That means our derivative of this is going to be h prime of x equal to f prime of g of x basically, I don't know why they called it the chain rule. I'm guessing because you gotta like bring this one along like the next link in the chain, but I didn't name them. So let's just try an example. Let's say we have h of x is equal to x squared plus x to the power of 3 over 2. So let's say the way we interpret this is that our g of x is equal to x squared plus x, and our f of x is going to be x to the power of 3 over 2. So when you have f of g of x, basically g of x is this inner function here, which we put into here. That'll give us that. So by our definition of our derivative, we can do this. The derivative of our inner function is going to be 2x plus 1, and then of this one is going to be 3 over 2x 1 over 2. So now we can actually plug in our f prime of x, well, x squared plus x is equal to 3 over 2 times x squared plus x to the power of 1 over 2. Remember, we're just plugging that into here because that's the chain rule. G of x plugged into f prime of x. Our f prime is this. We're plugging in our g of x into there, multiplied by g prime of x, which is 2x plus 1. And there you have it. That is the derivative of that. Saves a lot of time just by looking at it. So let's do another one. We can do, let's try y equals u cubed minus 2u plus 1, but u is equal to 2 root x. So we're going to find the derivative dy over dx, but we also want to find it when x is equal to 4. We want to solve for that. So if we apply our inner function, this is our inner function, that is our outer function. So our outer function derivative is going to be 3u squared minus minus 2. And then our outer functions will be, let me just put this in bigger ones, 2 times, and then we have the square root. So square root is always, to the power of half, so because the 1 over 2 and 2 will cancel. So I'm just left with 1 over root x. And then I wanted to find it at 4. So x is equal to 4. And u is equal to 2 root x. So if we plug that in, if u equals if you plug 4 into that, the square root of 4 is 2. 2 times 2 is 4. So u is equal to 4. And 1 over root 4 is 2. So I'm left with 4 squared is 16. 16 times 3 is, well, 4 times 4 is 16 times 3. 48. 48 minus 2 is 46 times 46 over 2. I'm left with 23. And there we have it. Let's do one more. Let's do let's do this again. Let's say we have our inner function g of x is going to be x squared minus 5. G prime of x is going to be 2x f of x equal to x to the power of 7. F prime of x equal to 7x to the power of 6. So let's write that out using the chain rule. So I have f prime of x, but instead of x I want to put g of x, so x squared minus 5 to the power of 6 times the derivative of the inside, which is 2x. So the 2 will multiply times 2x times 7, so 14x times x squared minus 5 to the power of 6. And that's how simple it really is. So if you want to actually try this on your own, you can try this one. Let's see something. Say we have h of x is equal to 2x squared plus 3x minus 5 to the power of 4. Find h prime of x. And throw your answer in the comment section below. But that's all for this video, and I'll see you in the next one. Okay, so in this video we're going to be looking at velocity and acceleration. The reason why we're going to be looking at this right in the middle of our derivatives section is because derivatives are actually how we can calculate rates of change, and velocity and acceleration are indeed rates of change. So let's say you have a function that describes the distance. If you take its derivative, you're going to find the rate of change at which the displacement or the distance is being traveled. You'll have the velocity, and if you take the derivative of velocity at any given point as it's changing, that will give you the acceleration. And that is why we look at velocity and acceleration, because if you do the first derivative and the second derivative, that's how you get these. So speaking of first and second derivatives, let's actually just try an example. Let's say we have f of x equal to x over 1 plus x. I want to take the second derivative and I want to solve for x equals 1. So what I'm going to do, I could use the quotient rule, but I'm going to quickly use the product rule. And it's just quicker for me to do. So I should have the derivative of the first one, which is 1 times plus the derivative plus x actually times the derivative of that one, so that'll give me negative 1. Derivative of the inside. So I have 1 over x plus 1. No, I should have a negative. Negative 1 times x, so x in the numerator. So what I can do now is multiply this side by x plus 1 over x plus 1, which will give me x plus 1 over x plus 1 squared. So x will be cancelled out, so I'm just left with f prime of x equal to 1 over x plus 1 squared. So now I want to take the double derivative of that. Let me just rewrite this like that. X plus 1 what does that actually mean though? If we were to look at this, like that was just me taking a second derivative. Let's actually put some context into this. So let's say we have a function which is s of t equals 6t squared minus t cubed, and t is also greater than 0. So t is time and s is in meters. So what we want to do is find, well, this s being in meters, this is a function that describes the displacement. So now I want to find the velocity and acceleration at t equals 2. It's very simple. S prime of t is equal to 12t minus 3t squared. And if we plug in 2 into that, 12 times 2 is 3 times 2 squared. That should give me 12. It's 24 minus 12. So 12. And if we do the second derivative, which will give me velocity, I should get 12 minus 16. So if I plug in 2 into this, I should get 0, which will tell me that if this is the function for displacement at 2 seconds, at the second, oh, that's interesting to say, at 2 seconds, the velocity will be 12. Meters per second, and then here it'll be 0 meters per second squared. So let's see what else we can do here with this world problem. We can ask ourselves, we can ask questions like, let's see, what can you do with this? You can figure out at what time is the object at rest. So when an object is at rest, it means it's not moving, which means when our s prime is equal to 0. So 12t minus 3t squared. So you can actually just factor this out. So 3t should give me 4 minus t. 0 equals. So at t equals 0 and at t equals 4. So at these 2 points, the object is at rest. You can also figure out in which direction it's moving at t equals 5. And means that this velocity and acceleration, and you'll see that here we had a acceleration of 0. That's okay. That's not wrong. If something is moving at constant velocity, that means the acceleration is 0. It's not getting faster or slower. So that is correct. So what else do we have? Maybe I could leave you with something to try on your own. Say y equals x squared plus 1 over x squared. Find the second derivative and throw that into the comments. But for now, that's all for this video, and I'll see you in the next one. Okay, so in this video we're going to tackle optimization. So one thing that I want to quickly go over, the max and the min of any function. Say you have a function or whatever, it's modeled by f of x. We know that f prime of x at any given point, say here, is like the equation to the tangent line. So, with that being said, when you have something that is here at the exact max, the tangent line will actually be equal to 0. Same for a min. It will be 0. Remember that. That is because the rate of change at that point, when you do the line, the tangent line, that will be just a straight line. So, with that being said, let's get into a word problem. Let's say you have 800 meters of fencing, and you have a wall, or say like a road or something. Let's say this is already done. You want to make a rectangle of some sort in which the two sides are x and this. So this amount. So basically you want to maximize this area here, but those dimensions need to be, the same. It has to be a rectangle. So one thing we can say is that the length of this side is going to be 800 meters. Well, I don't need to write that. Minus 2x, right? So the area for this is going to be this function is going to be x, which is one side, times 800 minus 2x, which is also 800x minus 2x squared. So remember what I said in the beginning. The derivative of this will give us the maximum of this function. So if we do the derivative, it'll be 800 minus 4x. And if we set this equal to 0, solve, we should get 4x equals 800, x equals 200. So, what does that tell us? At 200, we're going to get 200 times 800 minus 400. That's just this one, minus 2x. So that should give me 80k meters squared. And there you have it. So x will be 200, and then here you'd have 400. That will give you the maximum possible area, the dimensions. So we can actually try a different one now. Let's do, this might be harder to draw. Let's say I have let's say I have this sheet that is 60 centimeters on one side and 30 centimeters on another side, and I want to make this sheet into a box. I want to fold it upwards. But I want to fold the edges by a certain amount of the same amount on every side. X on each side. But I want it in a way that will give me the largest volume possible when I fold this into a box. So I know that my box's height when I fold it will be X. My length will be 60. Let me write this somewhere else. Will be X. Length will be 60 minus what I'm going to lose here and here, 2x, and my width will be 30 minus 2x. So you know that the volume is going to be this formula, like the dimensions. So V of x, V of x is equal to x times 60 minus 2x, 30 minus 2x. And if we expand this, we can get 4x cubed minus 180x squared plus 1800x. And I guess you already know what we're going to do with this. We're going to get the max and the min, well in this case the max, so IV prime of x is going to be 12 360x plus 1800. I can actually factor out 812. So, if we set this equal to 0, the 12 will divide by both sides, and I'm just left with this x squared minus 30x plus 150. So I'm going to put this, I need to find these zeros for this. So if you remember in our old formula, we're going to use our quadratic formula, negative b plus or minus that should be it. So I should end up with x b squared, so 900 minus 4 times 1, so 4 times 150. That should give me 600. 900 minus 600. That should give me 300 over 2 times a, which is 2. So I'm left with x equals 15 plus or minus 5√3. So let's see, x will be about 23.7, or x will be 6.3. So I'm gonna go with this one because that one clearly is not feasible in our situation, because if you plug it into here, you're going to be in the negative length, so cannot be that, so it has to be 6.3. So if you actually plug in back into our v of x formula, so let's put 6.3 back into should get 5196. Should be centimeter cubed. So yeah, that is how we use optimization, using the min and max, using, the derivative, our rate of change at 0. So that is going to be all for this video, and I'll see you in the next one. Okay, so in this video we're going to be tackling exponential derivatives, or derivatives of the exponential function. So if you remember y equals e to the power of x, there's not much to this. So if you have y equals e to the x, the derivative of that is going to be e to the x. I'm not making that up. That is something you can look up. So let's actually just start doing some examples here. So say if I had y equals e to the 3x. In our last video we did derivatives of composite functions where we used the chain rule, in which this would be our internal function. I'll put an I there, and that would be our external function, where you would have f of x being I guess e would be that, or something to the power of f of x would be something to the power of, let's say, y to the power of 3x, and then g of x would be r logarithm. So that, ignore this, I'm not 100% sure about that. But if you were to do the use the chain rule here, you would basically do e to the 3x times the derivative of our external function, which is going to be 3. So our derivative is going to be 3e to the 3x, because, let me see if I can get this right, if f of x equals e to the g of x, and my g of x is going to be 3x. Yeah, that's how it's supposed to be. So f prime of x, which is that, is going to be f of x times hold on. Yeah, f prime times g prime of x, which is basically e to the g of, when it comes to, logarithms, exponential functions, you have e to the g of x times g prime of x. That's what I was trying to get at. So you can even do that with, say, e to the power of x squared minus x. Now you know how to do it. Just rewrite it and then multiply it by the derivative of the exponent, which is going to be 2x minus 1. Let's see what else we can do. Say we have f of x is equal to x squared e to the x. We can use the product rule here. So we can put the derivative was that? Let's try another one. F of x equals 3e to the x squared. Let's try to find f at negative 1, or f prime at negative 1. So, let's start by taking the derivative first. We can set the 3 aside and just do the derivative of e to the power of x squared. So we know that that's going to be x squared times 2x. So we should get 6x e to the x squared. And if you plug in a negative 1, you should get negative 6e. Because negative 1 squared will become positive 1e to the 1 is just e. And that'll become negative 6. So what else can we do? Let's see. While we're on the topic of exponents, I guess I could show you f of x equals b to the power of x. Let's see. If you have an exponent like this, then your derivative is going to be the ln of b times b to the power of x. So that's pretty straightforward, right? So if you have f of x is equal to 5 to the power of x, your f prime of x is going to be ln 5 times 5 to the power of x. Same with if you have f of x is equal to 5 to the power of 3x minus 2. You're going to have, let's see if we can use the, no, I guess not. I'm wondering if we can use the chain rule here. Because the f prime of x should give me, let's see, what do we have? 5. I know I have my ln 5 for sure. And then let's see if I can use the chain rule here, where I have f of x equal to 5 to the power of g of x, and g of x is equal to the exponent there, 3x minus 2. So if I use the chain rule, the x, then your derivative will be f prime of x equal to the original function g of x times the ln of b times g prime of x. And I guess that made sense earlier when it was just b of x, because you would have b of x times the ln b, and then the derivative would just be 1 anyways if it was an x. Okay, that makes much more sense. So, I hope that wasn't confusing at all. And yeah, I shall see you in the next one. Okay, so in this video we're going to start doing the derivatives of trigonometry or trigonometric functions. So, you know we have sine x. So if you have, let's just get right into it. If you have y equals sine x here, it's going to be, actually let me put it here, is going to be cos x. The derivative of sine x is cos x. So, you might wonder, what is the derivative of cos x? Well, you guessed it. Kinda. It's actually negative sine x. One thing to remember though, when you have sine x at face value, it is cos x. But we'll learn what to do when, you know, you have sine 2x or something. I'll get to that in a bit, but let's just try one. Say you have y equals cos 3x. Well, at that point, you're going to want to do the chain rule, where you have, well, let me just write it out, and you might actually just see what I'm talking. Actually, this may be easier to do if I explain it to you like this. If you have y equals sine and then a function of any kind, then the derivative of that is going to be cos f of x, or whatever was in there, times the derivative of whatever is in that function. Similarly with this again, comes straight from the chain rule, where you do your internal function and then your external function. And there you go. So when we have something like, you know, y equals sine x squared, the derivative is going to be really just cos x squared times the derivative of what's in there, which is 2x. That's it. Similarly, if you have y equals sine squared put that down, sine x. So that's what this is. So when you put this into the chain rule, then you're going to have dy over dx. The derivative will be 2u, which is, the derivative of this one, times cos x, which is the derivative of sine x, at which point u will become 2x squared cos x. This one's incorrect. Y equals oh no, I confused a lot of people. This is actually going to be y equals u squared, and u equals sine x. See, y equals, we're going to say u is the sine x, and y is equal to u squared. So the derivative of y is going to be 2u, as u squared becomes 2u. And then the derivative of sine x becomes cos x. Let's do another one. Let's do y is equal to cos of 1 plus x cubed. So let's start doing this one. Well, first, let's do the derivative of cos, which is going to be negative sine of 1 plus x cubed times the derivative of what's inside here, which will be 3x squared. And just simplify that. Negative 3x squared sine 1 plus x to the cube. And there you go. It's actually much easier than it looks. Say you have y equals e to the sine x plus cos x. Now let's do that. Remember our derivatives for exponential functions. You just rewrite the same thing. Sine x plus cos x times the derivative of the exponent, which is going to be sine x will become cos x, and we're adding cos x, but the derivative of cos x is negative sine x, so it's going to be, and there you go. It's just one step at a time. So before, I think I could add it to this video here. Obviously when we're talking about trigonometry, you cannot forget about tan x. So the derivative of tan x is actually sec squared x. Well, yeah, but I should clarify from that if you have y equals tan with a function here, then similarly So say we have y equals tan of x squared plus 3x, then you know your dy over dx is going to be x squared plus 3x times the derivative in there, 2x plus 3. Yep, that is correct. What else do we have? We can do another one. Say you have y equals sine x plus tan x all to the power of 4. Well, now we can do our chain rule. Bring the 4 down. Write this again. Tan x times the derivative of what's inside. The derivative of sine x is cos x, and the derivative of derivative of sine x is cos x, and the derivative of tan x we know is x squared x. Simple as that. Let's try one more. Y is equal to, say, x tan of 2x minus 1. So here we have clearly the product rule that we're going to try. So let's do dy over dx, and let's do the derivative of the first value, which is 1, times plus the x times the derivative of tan x over this entire function. You know what, I'm going to write it here, plus x times, so the derivative of tan x is 6 squared times 2x minus 1 times the derivative of what's inside, which is going to be 2. So now you can rewrite this as tan 2x minus 1 plus 2x 6 squared 2x minus 1. And there you go. That's how easy the trig ones are. If you want to try one on your own, you can do y is equal to 3 sine 5x tan 5x and find out dy over dx. And then just throw that into the comment section when you're confident. And yeah, that's all for this video. And I'll see you in the next one. Okay, so in this video we're going to be starting the vector section. So what is a vector? It is basically that, well, it's much more complicated than that. It's basically a mathematical quantity having both magnitude and direction. So a vector must have a magnitude and a direction. So in our case here, we have A and B, and we have a vector that says it's going from A to B. So this we will notate like that. such as if we were to use an example of magnitude and direction, we could say, a car. Going, say, 100 kilometers per hour east. In this case, this is the magnitude and that is the direction. So we are going to use before we begin using magnitudes, we need to learn everything about them. So let's go over some simple rules. So if this vector a to b here, and let's label it v, if that is v, then the same, let's say you have the same line going the exact opposite direction. This is negative v. So the magnitudes of these are the same, but their directions are opposite. So what else can we learn about these? Let's see. Let's pretend these two lines are parallel. So we have A to B and C to D. So we have one of them is AB. We could actually say that AB and CD are parallel to each other, as well as, let's say that their magnitude, so the magnitude we would note as A like that under these absolute signs. Same magnitude. So if they are parallel and they have the same magnitude, then we can say that AB is equal to CD. So vectors are only equal to each other if and only if they're parallel and they have the same magnitude. Remember that. Now let's go into some actual, let's mess around with this. So let's say you have one vector A, C, and you have another one A, B, and let's say there's an angle between these two, and lowercase a dictates the magnitude. Well, not sorry, lowercase a I'm using to say that is the vector. So what am I going to do here? Basically, in math, when you have two vectors, you could actually add them and say that, if you were to put this vector here and move it up here, that is your sum of these two vectors. So if this is 1, that's 2, this is 1 plus 2, and that brings us to the parallelogram law, stating that if you have this, then A and B then you have, let's pretend that there's this little b here. this little A here. You could go actually either way. You could go from the top or the bottom. That is the same as that. That is the same as that. If you wanted to add these two vectors, you can go this way first, then up, or that way first, then up. But basically, you'd get to this part here. Let's pretend it's a perfect parallelogram. This would be A plus B. And that angle here that we had, theta, this is obviously 180 minus theta, because 180 is that, so the angle of that is theta, and this is going to be 180 minus theta in the parallelogram. This angle is the same as that angle, and that's why we have that. So we can actually write out A plus B is equal to the vector AB plus B to D, which is from here to there, equal to a new vector A to D, which is that middle one there. So what else can we do? We can do vectors in the same direction. When you have two vectors, say they're both going just straight that way, say F1 and F2, then you have the sum of R. I'm just making these letters up as I go. The magnitude adds F1 plus F2 is equal to the magnitude of, and the direction stays the same. So maybe we can do an example here to kind of drill in the point. Let's say we have that's kind of long. A to D, and we have a B here. And let's say that's my A vector, and that's my B vector. And I'm gonna give it an angle of 60 degrees. So let's say that the magnitude here is 3, and the magnitude here is 2. Now I want you to find out what is A plus B. So let's start doing that. So remember our parallelogram law. We're going to, if this is 60 degrees, then I basically want to find this one. Let's pretend that's a straight line. And that is A plus B, right? And I know the angle here is 120 degrees. And that's the same as B, which is there. And this is A, which is the same as that. So we know that A is 3 and B is 2. So when we use the parallelogram, we could basically basically use the cosine law. If you remember, we have, like if we were to redraw this, we basically have this side and that side, the angle of 120. So I know that this side is equal to 3 and that side is equal to 2. And I want to find that out, right? And my x is basically this. Well, you should write out the cosine law in case you forgot. So here my B and my C and this angle is capital A and that's my lowercase a. So when I put this in, I'm going to get x squared equals, say, 3 squared plus 2 squared minus 2 times 3 times 2 times cos of 120. And remember, I'll do it step by step. 9 plus 4 minus 2 times 3 is 6. 2 times 3 is 6. 6 times 2 is 12. Cos of 120 is negative 1 over 2. You should be able to do that in your head. If you remember, I did a video on how to quickly find those special angles. So that is going to be 13 minus, what's that going to be? Negative, so positive. 6. X squared equals 19. So x is equal to root 19. So basically, so that is how we add vectors. Similarly, if you had, say, a and you wanted to find out, minus. So instead of adding, now we're subtracting. What we actually do is just take this up here and convert it into this a. Let me write it below here. Instead of doing this we are going to do the subtraction, but in simple terms, we just turn this b into a negative b, and now we just add like that, and that is now my a minus b. So that is very straightforward. I hope this is somewhat very complicated. Not complicated, but you just have to be very good at visualizing, things in the lines in the 3D space. So, hopefully we can get more into it, but for now, I'll leave it at that. And yeah, that's all for this video, and I'll see you in the next one. Okay, so in this video we're going to tackle vector properties. So we're going to go over a few rules and laws that will be used in calculus when we are dealing with vectors. More specifically, when we're dealing with vectors, algebraically, or when we want to simplify algebraic expressions, when we want to add or multiply, vectors. So let's write down some rules. So let's say you have vector A and you have a vector B. This is called the commutative property of addition. Which basically states if you have a vector A and B, this can also be written as B plus A. Because remember, when you want to add this one to that one, it's the same as adding that one and this one. So, that is one. The second is the associative property of addition, which is, remember, from our polynomials. Actually, that was a while back. Let's say you have these three. Well, this is the same as saying that this is the associative property, implying that these two are associated. That's the same as these two being associated in this expression. We also have the distributive property of addition, and that is going to be if we have a k, which is a number, and that's being multiplied by this, the distributive property. If you remember when we covered multiplying binomials, k can multiply into this binomial to give us ka plus kb, where k is any real number. What else do we have? We have adding a zero vector, which is pretty straightforward. If you add a to a vector of 0, that is still a. What else do we have? We also have the associative law for scalars. And this basically says that if you have m multiplying times that, m using mn times a. And then the final one, I guess, we have is the distributive law for scalars, which is m plus n times the vector a. This is going to be m a plus n a, the distributive law. So, if you, well, I guess we could do an example here. We can do a few examples. Well, let's do 2 examples here. Let's do this one using these laws that we've learned so far. Let's say we have 3 times 2a plus b plus okay. Now, all I want to do now is simplify this expression. And this is going to be very straightforward. So let's open up this first using the distributive property. So that's going to be 6a plus 3b plus 3c minus, I'm multiplying a minus 1 into here, minus 3b plus 2c. Now we can start moving them around using the commutative property. It's hard to say. Plus 3b, and then we have minus 3b plus 3c plus 2c. So, and I know it looks pretty straightforward just to start adding them, but I want to show you the distributive property for scalars, which is that and that. So now we have 5a plus 0b plus 5c, and 0b is basically the same as this. It's a 0 vector, so we can get rid of that and we're left with 5a plus 5c, or it could also be 5a plus c, whichever one you want. We could do another example. Say you want to do x is equal to 3i minus 4j plus k. And let's say y is equal, I'll put them here. Y is equal j minus 5k. And let's say we have z, which is equal to negative I minus j plus 4k. x plus y. So if we write out x plus y, it's going to be, 3i minus 4j plus k plus j minus 5k. So again, if you were to open this up, you would get 3i minus 4j plus k plus j minus 5k, and that would give you have 3i, and then you have j plus negative 4j plus j. That would leave you with negative 3j, k minus 5k. That would be negative 4k, and that's your answer. You could also do the same except x minus y. But when you open up the brackets, now these are negative. The sign flips for that one. And now you're left with let's see, 3i stays. We have negative 4j and a negative j, so that becomes negative 5, and then we have k and 5k. That becomes 6k. Now we can do one that's a bit more complex. Let's try x minus 2y plus 3z. So this is going to be a long one. So remember, our x is 3i minus 4j plus k minus 2 times y. And our y is j minus 5k. Where are you? Let's take this. What was it? Plus 3. Negative I minus j plus 4k. So let's open this up. So we have 3i minus 4j plus k minus 2j plus 10k. And what else? Negative 3i 2j minus 3j. So that in total will give me negative 9j plus 13k. Sorry, I jumped the gun there. Not 13, I missed this one too, so 23. So yeah, it's actually very straightforward to do these things. If you want to try one for yourself, you can try this one and put it in the comments, see what you get. So this is all one. You can try that on your own. 3 times a minus 2b minus 5c minus 3 times 2a minus 4b plus 2c minus a minus 3b plus 3c. So that will conclude today's